Hello, everyone. This is the projectile motion examples answer solutions. Starting with number 3, an artillery shell is fired with an initial velocity of 100 meters per second at an angle 30 degrees above the horizontal. The first thing I'm going to do is I'm going to draw a picture to kind of get a sense of what's going on and take the velocity vector, its initial velocity vector, and break it down into its components. So here I have my projectile, my x and my y direction. It's initially at ground level, and then it's fired at 100 meters per second at an angle of 30 degrees above the horizontal. And I'm going to take that and break it down into its components. So in the x direction, it's moving at a velocity of 86.6 meters per second. And in the vertical direction, it's moving at a velocity of 50 meters per second. So now that I have those pieces of information, the first thing part A asks for is what is its position and what its velocity after 8 seconds. So I'm looking for a horizontal distance and also a vertical height that the object would be at. Its position horizontally is relatively easy to solve for. The change in the x position is equal to the velocity in the x direction multiplied by the time. So I take the 86.6 meters per second multiplied by 8 seconds, and it is 692 meters downrange. And then after 8 seconds, I'm switching gears into looking at the vertical, looking for the change in the y. I start plugging in the y information that I know. It's moving upward of 50 meters per second to start with. This is a positive, multiplied by 8 seconds. Minus 4.9 meters per second, that's 9.8 times half, and it's negative. And then multiplied by 8 seconds squared. So the first part's 400 meters, this part is 313 meters, and therefore after 8 seconds, it is still 87 meters above the ground. So the position is 692 meters downrange and 87 meters above the ground. To find the velocity of the object, I need to find what its horizontal component of the velocity is and what is the vertical component of the velocity at 8 seconds. So at 8 seconds, I know that the horizontal motion is still 50 meters per second, and it's still all horizontal. It's still in the positive direction. However, after 8 seconds, the velocity in the y direction is no longer the... Wait a minute. Oops. The velocity in the x direction is 86.6 meters per second. Please excuse the mistake before. So therefore, that particular part is still consistent. It's still moving at a constant velocity, I should say. However, in the y direction, the velocity is no longer 50 meters per second. The final velocity is equal to the initial velocity plus the acceleration multiplied by the time. I know the initial velocity is a positive 50 meters per second minus the negative 9.8 meters per second times 8 seconds. So the final velocity in the y direction is negative 28 meters per second. What that tells me is that it's moving in the downward direction now. So at this point, I'm simply going to redraw the vectors. I have the 86.6 meters per second horizontal. I have 28 meters per second in the downward. I'm going to use a little bit of a little Pythagorean theorem and a little trig to find that velocity vector, which would be 91 meters per second at 18 degrees below the horizontal. Part B asks for the time required to reach its maximum height. You only have to consider the motion that's going on in the vertical direction in order to solve this. I know that the initial vertical motion of the object is 50 meters per second upwards, and I know when it finally gets to the peak, the velocity at that point is going to be 0 meters per second. So, and I know that the object's velocity is going to constantly change at a rate of 9.8 meters per second every second. So how long is it going to take to go from 50 meters per second down to 0 meters per second if I take away 9.8 meters per second every second? So what you see here is the mathematical setup. The time is the final velocity minus the initial velocity divided by the acceleration. So I have my final velocity at the peak is 0 minus 50 meters per second divided by negative 9.8 meters per second gives me a time to the peak of 5.1 seconds. Finally, part C asks for the horizontal range, or how far does the projectile move. I am assuming that it's going to land at the same height that it started from. I don't indicate that it's going to hit something or try to compare its height somewhere else. So what is the horizontal range is once it hits on the flat Earth once again, how far horizontally has it moved? So since I solved for the time in part B, I can just double that time in order to get the total time in the air. So the horizontal range is just the velocity in the x direction multiplied by the time in the air. I have 86.6 meters per second times 10.2 seconds gives me a horizontal range of 884 meters. Okay, I can hear some of you saying, Mr. Lavering, that's not how you solved it in class. Okay, yep, that I used some of the symmetry of the problem. Hopefully that made some sense and how to figure out what the total time was, assuming that it is landing on a flat level plane. I guess more to model how I've done out in class. I'm going to use the third kinematic equation here. The change in the y is equal to vy times t plus 1/2 at squared. And I know that the initial and final heights are going to be the same, so the change in the y direction is going to be 0. I can plug in the values that I have. 0 meters is equal to 50 meters per second times t, minus 4.9 meters per second multiplied by t squared. This is a quadratic with the c being 0. I can pull a t out of this. So the two answers I end up getting in this case are t is equal to 0 seconds, which hopefully makes sense. There's one solution. The cannonball or the object starts at the initial height at time is equal to 0. And then the other one is solving what's in here. 50 minus 4.9 equals t. What does the t value have to be to make everything in the parentheses equal to 0? That would be 10.2. So therefore, that is the same time that we had arrived at in the previous solution. But Mr. Lavering, I saw this equation on the internet and you gave me the same answer, even though I really didn't understand how it worked. That the total time in the air is equal to 2 times the peak time, which sort of looked something like one of the two forms that I've sat there. And is it the same thing? And the answer is, well, yes, it is the same thing. If you look back at the mathematics that we had done for the first time I solved for the peak time, I literally used this part of it, the Vy over G, because the final velocity was 0. So it was just the velocity in the y direction divided by the acceleration gave me the peak time, and then doubling that. That's literally what this equation is. So, or in the solution that was the second way to arrive at the time, this is literally the same thing as what's in the parentheses. I hope this was helpful. Thanks for watching.